Good morning, sir. My name is Nandina. I am from CSC B section, and the subject name is Basic Electrical and Electronics Engineering, and the subject code is 234G1A05A8. And today my topic on electronics subject is logic gates. So, introduction to logic gates is our first topic, and next topic is types of gates, and there are AND gate, OR gate, NAND gate, NOT gate, NOR gate, XOR gate, XNOR gate, and conclusion about logic gates. First, we are moving to the introduction to logic gates. A logic gate is a hardware implementing a Boolean function. That is, it performs a logical operation on one or more logical inputs and produces a single logical output. It takes more number of logical inputs, but it produces only single logical input. Logic gates are primarily implemented using diodes or transistors acting as electronic switches, but it can also constructed using vacuum tubes, electromagnetic relays, pneumatic logic, optics, molecules, or even mechanical elements also. With amplification, logic gates can be cascaded in the same way that Boolean functions can be composed, allowing the construction of a physical model of all Boolean logic. Next, therefore, all of the algorithms and mathematics that can be described with Boolean logic only. The three basic logical operations are AND operation, OR operation, NOT operation. There are four combinations compared to this. NAND and NOR gates are universal gate. These are also a combination of two gates. NAND is not and NOR is not and OR. XOR gate is called exclusive OR and XNOR gate is called exclusive NOR gate. Next, first we are moving to the AND gate. The AND gate is an electronic circuit that gives true output. Output 1 only if all its inputs are true. A dot is used to show the AND operation. That is, A dot B is the operation. So this is the diagram about AND gate. This is the truth table of AND gate. So suppose we give A value is 0, B value is 0, the output is also 0. Suppose A value is 0, B value is 1, output 0. A value is 1, B value is 0, output is also 0. But A value is 1, B value is 1, it takes output 1. Next, we are moving to the OR gate. The OR gate is an electronic circuit that gives a true output 1 if one or more of our inputs are true. A plus is used to show the OR operation. So in this also, we give A output here, B output here, it takes the output C. In this also, suppose we take A value is 0, B value is 0, C value is 0. A value is 0, B value is 1, it takes the output 1. A value is 1, B value is 0, output comes is 1. A value is 1, B value is 1, and the output is 1. Next, we are moving to the next gate, that is NOT gate. The NOT gate is an electronic circuit that produces an inverted version of the input at its output. It is also known as inverter. If the input variable is A, the inverted output is known as NOT A. This is also known as A dash or A with a bar over the top. Suppose we give output is 0, it takes output 1. Input is 1, it takes output is 0. So this is the NOT gate diagram, and this is the truth table of NOT gate. So A value, this is the output, A dash value is output and A is input. We give input 0, it takes output 1. We give input 1, it takes output 0. Next, we are moving to the next gate, that is NAND gate. This is a NOT AND gate, which is equal to a NOT AND followed by a NOT gate. The outputs of all NAND gates are true if any of the inputs are false. The symbol is an AND gate with a small circle on the output. The small circle represents an inversion. It is also look like a AND gate, but the small difference on AND gate and this gate is a small circle on the output. That is the difference between a AND gate and NOT gate. And NAND gate is only combination of NOT AND gate, and that's it. And if we take input A value is 0, B value is 0, it takes NAND output is 1. Suppose we give A value is 0, B value 1, it takes output 1. A value is 0, B value is also 0, it takes output 1. A value is 1, B value is 0, it takes output 1. And finally the output A value is 1, B value is 1, and it gives the output 0. So this is the NAND gate. And next, NOR gate. This is a NOT OR gate, which is equal to an OR gate followed by a NOT gate. The output of all NOR gates are false if any of the inputs are true. The symbol is an OR gate with a small circle on the output. The small circle represents inversion. This is also looks like a OR gate. It gives here A output, B here B output. It takes the output. So this is also a combination of NOT and OR gate. There is a it's look like a OR gate circuit diagram. So we take a value is 0, B value is 0, it gives output 1. And next A value is 1, B value is 0, it gives output 0. A value is 0, B value is 1, it gives output 0. A value is 1, B value is also 1, it gives output 0. Next we are moving to the next stage, that is XOR gate. The exclusive OR gate is a circuit which will give a true output if either but not both of its two inputs are true. An N-cycle per sign is used to show the XOR operation. This is the XOR operation electronic circuit diagram. It is a exclusive OR gate. So we take output A value is input A value is 0, B value is also 0, it gives output 0. A value is 0, B value is 1, it gives output 1. A value is 1, B value is also 0, and it gives again 1. A value is 1, B value is also 1, it gives output. Same values gives the 0 value, and different values gives the 1. So next we gate is XNOR gate. And the exclusive NOR gate circuit does the opposite to the XNOR gate. It gives a false output if either but not both of its two inputs are true. The symbol is an XOR gate with a small circle on the output. The small circle represents inversion. So it looks like a XOR gate. There is no difference between XOR and XNOR gate. There is only difference between XOR and XNOR is only the small circle. It represents a inversion. So we suppose we take A value is 0, B value is 0, it gives output 1. A value is 0, B value is 1, it gives output 0. A value is 1, B value is 0, equal to output is 0. And then A value 1, B value is also 1, it gives output 1. And this is about all the gates. Finally we go to the conclusion of logic gates. Logic gates are the building blocks of digital circuits. They perform basic logical outputs functions that are essential for digital computing. Each logic gate has truth table that defines its output for every possible input combination. Logic gates can be combined to create more complex circuits like multiplexers, demultiplexers, encoders, and arithmetic logic units. The operation of logic gates can be described using Boolean algebra, where variables represented binary numbers. Binary values can represent logic gates only. Logic gates only represent binary values, that is 0 ones only, and operations correspond to logic gates. And thank you, sir.